Welcome to my channel, Chemistry Revision. We'll kick off with 2022 March Chemistry Revision paper, paper 1, and I'll start with the first 10 questions. The first question was, draw a label diagram showing the atomic structure of magnesium. So as you can see, you've been given the mass number of magnesium, which is 24, and its atomic number is 12. To draw the atomic structure of magnesium, you need to know the information in the nucleus and in the energy levels. So in the nucleus, normally we have the neutrons and the protons. So we have to indicate their numbers inside the nucleus. To get the atomic number, to get the proton number, which is the same as the atomic number, which is 12, we just put there 12p. 12p is the proton number. And then to get the neutrons, we get the atomic number from we subtract the atomic number from the mass number. That will be 24 minus 12. We get 12. And then we go on and indicate 12n, which is 12 neutrons. So with that, we will have obtained the information in the nucleus, which is 1 mark for the same. And then we go to the energy levels. To get the information in the energy levels, you have to write the electron configuration of magnesium. Having known the atomic number, which is 12, we have to write the electron configuration of magnesium, and that will be 2.8.2. So we start off with the first energy level, and in the first energy level you indicate 2 electrons. As you can see, I've put 2 electrons. You can use dots or you can use crosses, and since electrons occur in pairs, I've put the two electrons together. In the second energy level, you can see we have 8 electrons. The 8 electrons, you can put them in 4 pairs. So that is my first pair, second pair, third pair, and the fourth. That is a total of 8 electrons occupying the second energy level. And lastly, the third energy level, we have 2 electrons. I've indicated them as a pair. So that gives us the energy level information. So the total marks 2 are distributed, 1 in the energy level and the second one in the nucleus. Let's move on to part B of question 1. The atomic number of phosphorus is 15. Draw a dot and cross diagram for the compound formed when phosphorus reacts with chlorine. Atomic number 17, only 1 mark. So here you have to understand that you are drawing a compound formed when phosphorus and chlorine react. So phosphorus atomic number is 15, configuration will be 2.8.5, and from that you can tell it is a non-metal because it will react by gaining electrons. Chlorine, on the other hand, whose atomic number is 17, has configuration 2.8.7. That means also it is a non-metal because it will gain electrons to become stable. So when non-metals react, they do so via a bond called covalent bond, and therefore we are going to have what we call sharing of electrons. To know how the electrons are going to be shared, you have to draw the chemical formula of the compound that will be formed, and that is phosphorus chloride. Phosphorus chloride formula is there. You can see we have 1 phosphorus atom combining with 3 chlorine atoms, and in this case it means that our phosphorus, which is a single atom, will be at the center and it will be surrounded by the 3 atoms of chlorine. Then you go ahead and show how the distribution will take place. Remember, phosphorus is only requiring 3 electrons to become stable, and those 3 electrons are the ones which are going to be shared with chlorine, and that means that 2 of its electrons will be unshared, and that means it will remain inside its energy level. We call them the lone pair or the unshared pair. You can see that. Remember, you have to have a key, and in my key for phosphorus I've used dots, and for chlorine I have used crosses. That will guide even the examiner when marking, to avoid confusion. Otherwise you'll find yourself putting dots for both the 2 atoms or X's for both of the atoms. So they have to have a key to distinguish the 2. Next we go to chlorine. Chlorine only requires one electron to become stable. Therefore, it will donate one electron for sharing with phosphorus. And as you can see, I've indicated X on each of this overlapped circle. So that means that the dots are being contributed by phosphorus and the X's by chlorine. And if chlorine is only donating one electron for sharing, it means that the remaining 6 are going to remain in its outermost energy level. And you can see I've put the 6 electrons outside. Don't forget to indicate them, otherwise you'll be penalized, because if you do not indicate them, it means that chlorine only has one electron. Remember, only one is being shared. So a total of 7. You can see we have 7 X's. And now when it combines with the one contributed by phosphorus, they become 8. And eventually our chlorine becomes stable. You do the same for the remaining 2 chlorine atoms, and your compound will be stable, as you can see. So if you consider each of the atoms in the compound, let's start with phosphorus. You can see phosphorus has 1, 2, 3, 4, 5, 6, 7, 8. And indeed it means that it's now stable. I'll only look at one of the chlorine atoms. Let's look at this one. 1, 2, 3, 4, 5, 6, 7, 8. Chlorine now is stable. So that is our compound of phosphorus chloride, formed when chlorine and phosphorus reacts. It doesn't require a lot of work. You can see it's only 1 mark, so don't use a lot of time there. Let's move on to question number 2. State the condition under which a Bunsen burner produces a luminous flame, for 1 mark. So a Bunsen burner produces a luminous flame when the air hole is fully closed. Remember, this is a luminous flame. So our answer is when the air hole is closed. When the air hole no more discussions there, just that. Move on to question number B of 2. Write an equation for the reaction that takes place in a luminous flame, assuming the laboratory gas is butane. So here we are doing what we call combustion. Butane is an alkane, and remember the general formula of alkanes is CnH2n plus 2. So that means our butane will have the formula C4H10. Butane is a gas at room temperature. So the reaction that will take place when a luminous flame is burning butane, then it means that it is combining with oxygen gas. So the reaction that will take place will be combustion. Therefore, butane will burn to produce a colorless gas called carbon 4 oxide, and steam, which is water vapor, which is also a gas. Remember, for you to get your 1 mark, half of the mark will be from the state symbol. The half one will come from balancing of the equation. So to balance this, we'll make sure that our carbon atoms are balanced, and to avoid fractions, I'm going to put 2 before butane, so that my carbons are 8 in number, and here I'll also put 8, so our carbon atoms are all balanced in each side. Next, let's deal with hydrogen. Hydrogen I have 10 times 2, which is 20, and on my right side I have to also ensure that it is 20, and to do that I just put 10 there. So our hydrogen atoms are balanced. We wind up by looking at oxygen. On our left we have only 2 atoms. On our right we have 16 plus 10, which is 26. To make sure that also this side you have 26, I just take 13, which I will multiply by 2, we get 26. So that is a balanced chemical equation when butane is burnt using a luminous flame. So their luminous flame is our source of heat, and butane is combining with oxygen, a process called combustion. So just write a balanced chemical equation. Don't forget to put state symbols. We move on to part C. One of the regions in the non-luminous flame is the unburnt gas region. Describe how the presence of this region can be shown using a wooden splint. So this is Form 1 work. Remember, in a non-luminous flame, the unburnt gas zone is found in the middle part, the lower middle part of the flame. So here you draw using a pencil. I can draw your, this is my wooden splint, and when we insert the wooden splint in the unburnt gas zone, then it means that the middle part will be uncharred, whereas the outer part will be charred. So you just indicate it that way, and then you make sure that it is labeled. So remember, we are describing that by use of a what? A diagram, and we are using a wooden splint. So what is going to happen to indicate here is that this part is charred. Charred means burned, and then the middle part, due to the unburnt gas region, is going to be uncharred or unburnt. If this disturbs you, you can just write burnt. So that is our wooden splint. Showing what will happen when a wooden splint is placed in the unburnt gas zone. Nice. Let's move on to question number 3. In question number 3, you're being asked the elements sodium, magnesium, and aluminium belong to group 1, 2, and 3 respectively. Select the element with the highest electrical conductivity and give a reason. Electrical conductivity is the ability of a substance to conduct electricity. So here, to give the correct answer, you have to know the number of delocalized electrons each one of them have. So starting with sodium, we know that sodium is number 11. Therefore, its configuration is 281. On the other hand, we have magnesium. Magnesium is 282, and lastly we have aluminium, which is 283. So the one which has more delocalized electrons among those three is aluminium. So to answer our question, the element with the highest electrical conductivity will be aluminium. So our answer is aluminium, full stop. And you give a reason. You say because it has more delocalized electrons than sodium and magnesium. That will be our answer. Next, we move on to part B of question 3. Complete table 1 to show the products of electrolysis for concentrated sodium chloride and molten sodium chloride. This is form 4 work. So our first electrolysis, electrolysis form 4 work compound. The first one is concentrated sodium chloride. When concentrated sodium chloride electrolysis. We are going to have sodium ions. You can even just write here. We'll have sodium ions, we'll have hydrogen ions, we'll have chloride ions, and hydroxyl ions being formed. So because the electrolyte, we have two electrolytes there, that is sodium chloride and water. So when the electrolyzes, we'll get those ions. But the key thing here is that it is concentrated. So we'll start by looking at our anode. So the ions which will migrate to the anode will be chloride ions and hydroxyl ions. Chloride ions and hydroxyl ions. So since this compound is concentrated, the ions which will be discharged will be chloride ions. And chloride ions, when they move to the anode, they will form chlorine gas. They'll form chlorine gas. So the product here will be chlorine. Remember, they want you to show the product that will be formed. Next, we move to the cathode. And to know what will move to the product that will be formed at the cathode, you have to look at the ions. We have sodium ions and hydrogen ions. These two, when they move to the cathode, remember, chlorine has been discharged, so the solution becomes a bit dilute. So what is going to happen is that the hydrogen ions are the ones which are going to be discharged, and on being discharged, they'll give us hydrogen gas. So the product at cathode will be hydrogen gas. Let me add here gas. Lastly, molten sodium chloride. So for molten sodium chloride, we have two ions. One is sodium ions. Remember, this is a binary electrolyte. I have sodium ions and chloride ions. So at anode, the chloride ions are going to migrate there, forming chlorine gas. So that will be our product at anode. On the other hand, at cathode, you're going to have sodium ions moving there. So we're going to have sodium metal. Nice. So for 2 marks, we get that. Let's move on to question number 4. A small piece of sodium metal was placed in a beaker containing pure water. State 2 observations made during the reaction. Remember, it's only 1 mark. Even if you have so many points, you just indicate 2 of them. So 1, which is the major one, you'll see sodium metal darting on water. So you say it darts on water. The second one, which will be clear, you'll see it melting into a silvery ball. So you say it melts into a silvery ball. So there are other observations which will be indicated, but for the sake of this exam, you only put the correct 2. Other ones will be a hissing sound will be produced, and you'll also see a colorless gas being produced. So for each, you get half a mark. Let's move on to part B. State and explain another observation made when a drop of phenolphthalein is added to the mixture. So here you have to know that phenolphthalein is an indicator, and when sodium is put in water, it's going to dissolve to give us an alkaline solution, and therefore we expect a pink solution to be formed. So our statement will be the solution turns pink. The solution turns pink. That is state. Then you go ahead and explain the observation. So the observation is explained by saying this is because sodium reacts with water to form an alkaline solution. Sodium reacts with water to form an alkaline solution. Part C. Explain why it is not advisable to carry out this experiment using potassium metal. So remember, both potassium and sodium are in group 1. However, this reaction is not encouraged to be done using potassium metal, so it's not advisable. And we say this is because potassium being more reactive will react explosively with water. So you do not want to explode. We don't want to carry out explosive reactions in the laboratory. That's why it's not advisable. Moving on to question number 5. Question number 5 is describe how a pure sample of copper 2 nitrate crystals can be prepared using recycled copper wire. So here we are making a soluble salt of copper 2 nitrate, and the best option is to use a reaction between an acid and a base. So the acid which automatically you have to use is nitric 5 acid, and the base has to be your copper base, and the copper base that you're going to use will be copper oxide. However, we have only been provided with recycled copper wire, and in this case the first thing we have to do is to heat our recycled copper wire to obtain copper oxide. So in our first description we just say heat the copper wire to obtain copper 2 oxide. Next, we use our dilute nitric 5 acid so that we get copper 2 nitrate. Nitrate comes from nitric 5 acid. So let's use 50 cubic centimeters. You can choose whatever volume you want. So the next thing we do is you measure 50 cubic centimeters of dilute nitric 5 acid in a beaker. The next, we put the copper 2 oxide from the above copper 2 oxide in the acid. And stir till in excess. How will you know that it is in excess? You'll know that it's in excess when some of the copper 2 oxide remains, and then that will indicate that your reaction has come to an end. So having excess copper 2 oxide will mean that you have to separate the two, and the best thing to do is to filter. So in your fourth step, we just filter to obtain copper 2 nitrate. Then next That is our step 4. In our step 5, remember they want crystals. So step 5, you transfer it into an evaporating dish. And heat to saturation. After that, in our step 6, our final step, we cool the saturated solution to obtain copper 2 nitrate. Crystals. That process is called crystallization. So here we are not using copper metal directly, the recycled wire with nitric 5 acid, because we know that copper is below hydrogen in the reactivity series, therefore it cannot displace hydrogen from nitric 5 acid. So you have to use its base. Moving on to question number 6. The following apparatus and chemicals are used to investigate the percentage of air used when iron rusts. So we have iron filings, 100 ml measuring cylinder, a trough, and water. Draw a setup of the experiment. This was Form 1 work. So we have to show or in investigating the condition that the percentage of air which is used when iron rusts. So we'll start by drawing our trough. Remember to use a pencil. If you use a biro pen, you're going to be penalized. So that is our trough. The next thing we have to do is we invert our measuring cylinder, our 100 ml measuring cylinder, into this trough. Remember the trough contains water, but I'll indicate the water later on. So this is our measuring cylinder. Don't forget to show the calibrations, because all of us know that a measuring cylinder is calibrated. So it has to have that. And then we have, I'm now going to indicate the water. And remember our measuring cylinder is moist, so that it can trap some iron filings. So the iron filings will be trapped beneath the measuring cylinder. So you'll have to label it that way. And then I now indicate my water in the trough like that. I'm imagining that it's just the beginning of the experiment, so the movement has not yet started, so the level of water is uniform. So you don't forget to show that our diagram is not hanging in air, it is on a bench. Then you go ahead and now label your diagram. This is our water, this is our trough, this is our measuring cylinder, and this is our iron filings. Just like that, we get our 2 marks. Moving on, write an expression to show the percentage of air used in how the percentage of air used is calculated at the end of the experiment. So we can say initial volume of air minus final volume of air. You divide all these by initial volume of air, then you multiply that by 100, because you're getting the percentage. You don't just say A minus B over A times 100. No, you have to tell us what A is and what B is. So you can have your key if you want to use letters to represent your experiment. So that is the expression used to determine the percentage of air used during rusting. Moving on to question number 7. The figure 1 shows a graph of atomic radius of some group 1 and group 2 elements. So on our x-axis we have our x-axis and we have our y-axis. So you can see you have atomic radius and you have atomic number. So you're being asked, let's study lithium. You can see lithium has a higher atomic radius. It is higher than that one of beryllium. Whereas when you consider sodium and lithium, sodium has a higher atomic radius than lithium. On the other hand, you have beryllium, which has a lower atomic radius compared to magnesium. However, when you come to atomic number, sodium has a higher atomic number than lithium, whereas magnesium has a higher atomic number than beryllium. You can even check that here our magnesium is having atomic number 12, and on the other hand you can just extrapolate to get the atomic number of sodium. Let's go to the question. A, explain why the atomic radius of sodium is higher than that of lithium. Explain why the atomic radius, this one, the atomic radius of sodium is higher than that one of lithium. So remember, atomic number is the one that is directly proportional to the atomic radius. So here you just say this is because sodium has a higher atomic number than lithium. I'll stop just one more so you avoid a lot of explanation. You can contradict yourself. Next you go to magnesium. You explain why sodium has a higher atomic radius. Explain why sodium has a higher atomic radius than magnesium. So here you have to look at the same, but here we explain using the proton numbers. So we say this is because magnesium has more protons than sodium, hence its atomic radius is smaller than sodium. So here you are looking at the nuclear force of attraction. Predict the atomic radius of calcium. Predict the atomic radius of calcium. So here we are talking about the atomic radius of calcium. Remember, calcium is not indicated here. To get calcium, you have to roughly know that calcium is in group 2, and therefore we have to extrapolate our curve for these group 2 elements. And if we do that, you're going to find out that calcium being number 20, question is number 20, that is its atomic number. So we are going to find that it will be here. And since it's going to be there, then we are going to go to our y-axis, and we'll find out that it is roughly at 200. So find, come and say, predict the atomic radius of calcium. So we'll just say 200. Don't forget to put the units. You can see the units there was nanometer, so you see 200 Nm. That will be your answer. Question number 8. Compound D with formula C3H4 was reacted with excess hydrogen chloride gas. Give the name of compound D. So to get the compound's name, you have to know that here we're going to have an addition reaction. So we'll have C3H4 reacting with excess hydrogen chloride